Welcome to my online course in linear algebra for undergraduate mathematics. In this lecture, we are going to discuss about orthogonality and orthogonal complement. First definition is the orthogonality of two vectors in an inner product space. If X is my inner product space and XY belongs to capital X are two vectors, then X is said to be orthogonal to Y, denoted by X orthogonal to Y, if and only if inner product of X, Y is equal to 0. Next is a note. First one, X is orthogonal to Y if and only if inner product of XY is equal to 0. By second axiom in the definition of inner product space, we know that inner product of XY is equal to conjugate of inner product of YX. So I am writing here conjugate of inner product of YX is equal to 0. Again, from the complex analysis, we know that if Z is any complex number, then conjugate of the number will give me the number big. By using this property, since inner product space is a mapping from the space X cross X to the complex field C to C, complex number, inner product space is a complex number, so this is a complex number. If I take conjugate of conjugate, then I will get the number big. That is inner product of conjugate of inner product of yx is equal to my inner product of yx. In the right hand side, it is a conjugate of 0. 0 is a real number. For real number, then I will get the number big. From this, I can write y is orthogonal to x. Number 2, since inner product of x comma theta null vector, theta is my null vector, is 0. For all x belongs to x, it follows that x is orthogonal to theta for all x belongs to x. That is, every vector is orthogonal to null vector. Only null vector is orthogonal to every vector in that space, inner product space. Third one, if x is orthogonal to y, then we have by property to inner product of x comma y is equal to 0 and inner product of y comma x is equal to 0. Now find out the norm of x plus y square. By definition, it is equal to inner product of x plus y, x plus y, inner product of x plus y comma x plus y. By next expand this, that is x, take inner product of x with x, then take inner product of x with y, again take inner product of y with x, then take inner product of x with y. I can write this step. That is, first inner product of x with x, then inner product of x with y, this inner product of y with x, and inner product of y with y. Since inner product of xy is equal to 0 and inner product of yx is equal to 0, these two are my 0. These two are my 0. So I can write in place of inner product of x comma x, it is norm of x square. Again inner product of y comma y, here it is norm of y square. Again if you take inner norm of x minus y whole is norm of x minus y square, which is equal to my inner product of x minus y comma x minus y. On expansion, I will get this step, which using these values, I will get this norm of x square plus norm of y square. Thus, for any xy belongs to x, if x is orthogonal to y, then norm of x plus y square is equal to norm of x square plus norm of y square. This is my Pythagoras theorem. This theorem is known as Pythagoras theorem. Okay, this theorem is known as Pythagoras theorem. If you are asked to prove Pythagoras theorem in inner product space, you should prove this result. Prove this result. Prove this result. What is the meaning? That is, if x is this vector, this is that line. If this is my vector x, and this is my vector y. This is norm of x, this is norm of y, and this side is my x plus y, x plus y. This is norm of x plus y. That is, if this vector is denoted by norm of x, this vector is denoted by norm of y, and they are orthogonal, then the third side is given by norm of x plus y. That is, norm of x plus y square is equal to norm of x square plus norm of y square. That is, norm of x square plus norm of y square is my norm of x plus y square. Next definition. If X is inner product space and S is a subset of X, then S is said to be orthogonal set if for xy, for all xy belongs to S with X not equal to Y, X is orthogonal to Y. That is, inner product is equal to 0. Inner product of X comma Y is equal to 0 for all x comma y belongs to my S. X is orthogonal to y for all x comma y belongs to S with x not equal to y. An orthogonal set in an inner product space X is said to be orthonormal if this happens. Okay, norm of X is equal to 1 for all x belongs to S. Next is orthogonal complement. A subset S of S in an inner product space X is said to be orthogonal complement written as S orthogonal if it is orthogonal to each vector of S. That is, S subset of an inner product space, then then the orthogonal complement of S denoted by S orthogonal is the set of all vector in X which are orthogonal to each vector of S. That is, S orthogonal is the collection of all x's in X, capital X, such that X is orthogonal to Y for all Y in S. Next is a note. Let X be an inner product space and X belongs to capital X and S is a subset of X. Then X is said to be orthogonal to S if this happens. If X is orthogonal to Y for all Y belongs to S, written as X orthogonal to S. That is, S orthogonal is the collection of all x's in X such that X is orthogonal to S. Next is a result. First one, X orthogonal to Y if and only if alpha X is orthogonal to beta Y for any alpha beta belongs to C and alpha not equal to 0, beta not equal to 0. Second result, that X orthogonal to X if and only if X is equal to theta. And third one, X orthogonal to Y for all Y belongs to X if and only if X is equal to theta. X orthogonal to proof, first one, X orthogonal to Y implies if and only if inner product of X, Y equal to 0. Now, take the inner product of alpha X comma beta Y. If I show inner product of alpha X comma beta Y is equal to 0, then we are done. So, when I write inner product of alpha X comma beta Y, then using the property of inner product space, we can take alpha outside from here first element. Then when I take beta outside from the second element, it become beta conjugate, alpha beta conjugate into inner product of xy. Now this alpha x inner product of alpha x comma beta y is equal to 0 if and only if this inner product is 0. Therefore, alpha x is orthogonal to beta y if and only if x is orthogonal to y. Number 2, x is orthogonal to x if and only if inner product of x comma x is equal to 0. And inner product of 0, by the definition of inner product, this inner product will be 0 if and only if the vector is null vector. That is, only null vector is orthogonal to itself. Third result, third one, x is orthogonal to y for all y belongs to x. That means inner product of xy is equal to 0 for all y belongs to x. This implies by the property of inner product space, x is my null vector. That means only null vector is orthogonal to every vector in an inner product space. Next result. Let X be an inner product space and X is a subset of X. First one. Orthogonal complement of the null vector is equal to the whole space. What is the meaning? By definition of orthogonal complement, orthogonal complement of the null vector is equal to collection of all the x's in X such that X is orthogonal to the null vector. Here, by the previous result, this we know only null vector is orthogonal to every vector. X orthogonal to y for all y belongs to x. Then this implies x is the null vector. That is, every vector is orthogonal to null vector. So this collection will be the set X. Okay. Next, number 2, orthogonal complement of x is my null vector. That is, when I take orthogonal complement of the full space, it is a collection of all x's belongs to x, such that x is orthogonal to my x. So only null vector is orthogonal to every vector. Okay. So only null vector is orthogonal to every vector. So I am getting this theta. X belongs to x such that x is orthogonal to x. Only null vector, I will get only null vector. This is orthogonal to every vector in x. So x orthogonal complement of x is my theta, null vector. Third one, S1, S2 belongs to X, inner product space X with S1 subset of S2 implies S1 orthogonal complement of S1 is a subset of orthogonal complement of S2. Let X belongs to S2, orthogonal complement of S2. This implies X is orthogonal to S2 whenever the element belongs to the orthogonal complement. That means the element is orthogonal to the set. As S1 is a subset of S2, from the set theory we know that if some result hold for bigger set, then it will be trivially hold for smaller set. If this is S2 and this is S1, if some result fall in this bigger set, then it will trivially fall in the smaller set. That means this X is orthogonal to S1. This implies X belongs to orthogonal complement of S1. Since X belongs to orthogonal complement of S2 is arbitrary, and we have found that every element here belongs to S1 orthogonal complement. So this S2 orthogonal complement is a subset of S1 orthogonal complement. This is S1. This is S1. This is S1. Fourth one, that is orthogonal complement of S is the closed linear subspace of X. First, we are going to show that S orthogonal complement of S is a linear subspace of X. Then we will show that it is closed. That is, it will contain all its limit point. Proof. By definition of orthogonal complement of S, we know that orthogonal complement of X is the collection of all X belongs to X such that X is orthogonal to S. Obviously, S orthogonal is a subset of X. By necessary and sufficient condition for a non-empty subset S of a vector space B over the field F to be subspace 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 if and only if x comma y belongs to S, alpha beta belongs to F, implies alpha x plus beta y belongs to S. If anyhow I will show this condition, then this S orthogonal is my subspace, linear space, because a subspace itself is a vector space, so this is a linear space. For that, I have considered two element xy in orthogonal complement of S, and alpha beta belongs to C. If x comma y belongs to orthogonal complement of S, then x is orthogonal to S and y is orthogonal to S. For any element z belongs to S, I am considering the inner product of alpha x plus beta y comma z, which on expansion, that is first alpha x comma z, inner product of alpha x comma z plus inner product of beta y comma z. Again, using the property, I can write this alpha inner product of x comma z plus beta inner product of y comma z. Then, since z belongs to S and x is orthogonal to S, so inner product of xz is equal to 0, and inner y is orthogonal to S and z belongs to S, so inner product of yz is again 0, alpha 0 plus beta 0. By using the property of inner product space, it will be 0, as alpha beta belongs to C and 0 belongs to C. So for alpha 0 plus beta 0 is my 0. As z is therefore alpha x plus beta y is orthogonal to z, vector z. Since z belongs to S is arbitrary, so this element is orthogonal to every element to the set S. That is alpha x plus beta y is orthogonal to S. That is S or orthogonal is my linear subspace. Next, we are going to show that S orthogonal is a closed linear subspace. Okay. For that, I am considering a sequence Xn in S orthogonal such that Xn converges to X. Then I am going to show that this limit belongs to S orthogonal complement of S. Let y belongs to S be arbitrary. Since y belongs to S and xn belongs to S orthogonal, it follows that y is orthogonal to xn. As y belongs to S and xn belongs to S orthogonal, so y is orthogonal to xn for all n ranges from 1 to up to infinity. That means inner product of x and y is equal to 0 for all n. Now, modulus of inner product of x, y. I am going to check what is the value of modulus of inner product of x comma y, which is equal to modulus of inner product of x comma y minus, as it is 0, if I minus 0 from this, then this modulus will remain as it is. So in place of 0, I am writing this x n comma y. As this value is 0, this will not create any change here. So in next step, by using the property of inner product space, I can write modulus of inner product of x minus xn comma y. Again, by using Schwarz inequality, this is less than equal to inner product of x minus xn. Sorry, it is a norm of x minus xn, norm of y by using Schwarz inequality. As we know, xn converges to x as n tends to infinity, so this will be my 0. At as n tends to infinity, x minus xn will be goes to 0. So this tends to 0 as n tends to infinity. It follows that modulus of inner product of xy is equal to 0. That means inner product of xy is 0. Therefore, x is orthogonal to y. Since y belongs to S is arbitrary, so x is orthogonal to y for all y belongs to x. Not x, that is S. Thus, x belongs to orthogonal complement of S. So, S orthogonal is closed. Orthogonal complement of S is closed. Hence, orthogonal complement of S is the closed linear subspace of the inner product space X. Next, if S is a subset of X, orthogonal complement of S is a subset of X, and orthogonal complement of the orthogonal complement of a set is a subset of X. And we can write this in this way. Next theorem, if x1 x2 dot 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 xn is an orthogonal set, then norm of sum over I ranges from 1 to n xi square is equal to summation I ranges from 1 to n norm of x square. We know that some norm of sum over I ranges from 1 to n xi square can be written in this form: norm of x1 plus x2 plus dot 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 xn square. By definition of norm, we can write it as inner product of x1 plus x2 up to xn, comma x1 plus x2 up to xn. If I expand this, this will be this expansion will be like this: x1 plus x2 plus dot 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 plus xn, comma x1 plus x1 plus x2 plus dot 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 plus xn plus x2 plus dot 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 plus x1 plus x2 plus dot 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 plus xn, comma xn. Okay. In the next step, is this can be expressed in the form this. I'm doing for only this one. Similarly, you can expand it remaining terms. That is, this can be written as x1 comma x1 plus x1 x2 comma x1 plus dot 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 plus xn comma x1. Likewise, I will get for this term up to this one: x1 xn, this is inner product, then this is inner product of xn comma xn close. Except this, all these inner product are 0. All these inner product are 0, as this is an orthogonal set. Okay, so this inner product of xi comma xj is my 0 for all I comma j I not equal to g. Okay, this due to this region, except the diagonal element, all the remaining element will be my 0. For the second term, I will get this one: x2 goes on up to xn. Okay, since this is equal to my norm of x1 whole square plus norm of x2 square plus dot plus norm of xn square. So this is this one. In case of using summation, I can write this one. Any orthogonal set S of non-null vector in an inner product space is linearly independent. Here, this vector S is not mentioned. If S is, so we have considered this as infinite set. Let S be an orthogonal set of non-null vector in an inner product space. Then to show S is linearly independent, we will show every subset, finite subset of S, every finite subset of S is linearly independent. Okay, S is linearly independent. Suppose we are going to prove the case for infinite. For finite, we will similarly prove this one. That is, instead of finite subset, you should write this. Let x1, x2 dot xn be a subset of S. Here, I am proving for the infinite case. Every to show a set is linearly independent, I am showing that every finite subset is linearly independent. I am considering S to be an orthogonal set of non-null vector in an inner product space. I am considering x1, x2 dot xn be a finite subset of S. Suppose lambda 1, lambda 2 up to lambda n be a scalar such that in our linear combinations of this scalar with this vector is this is equal to null vector theta, here where lambda I, this lambda I, this is lambda I. Okay, lambda I belongs to C. Now take inner product of this vector with itself, that is lambda 1, inner product of lambda 1 x1 plus lambda 2 x2 plus dot lambda n xn lambda comma lambda 1 x1 plus lambda 2 x2 plus dot lambda n xn, which is this right hand side is the this vector is my null vector. So right hand side will be the inner product of theta comma theta. That is, in place of this I am putting the value, that is theta comma theta, and this is my 0 vector. If I expand this, then first will be this vector with this vector, again this vector with this vector, this term I am getting this term, then this term, finally dot I am getting this term is equal to my 0 vector. Now if I expand this, then I will get term like this. This expansion will be my this lambda 1 equal to x1 plus lambda 2 x2 plus dot plus lambda n xn comma inner product of lambda 1 x1, then this inner product. Okay, this is equal to lambda 1 x1 comma inner product of lambda 1 x1, then plus inner product of lambda 2 x2, then lambda 1 x1 plus dot plus lambda n xn lambda 1 x1 goes on. This, when I take outside lambda 1 from this element, it is lambda 1, from this it is lambda 1 bar, lambda 1 conjugate, not bar, that is x1 comma x1. Okay, so likewise for the second term I am getting lambda 2 lambda 1 bar but here I'm getting x2 comma x1 goes on dot 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 plus lambda n lambda 1 xn x1 inner product of x1. This is my by definition of complex number z1 bar is my modulus of z1 whole square. So this is lambda 1 square, and this is my norm of x norm of x1 square, and this since x2 x1 is this is an orthogonal set, this is equal to 0 and this is equal to 0, remaining all term will be 0. So this I will left with one term only. Okay, from this I will get one term, from this I am getting another term, from this I am getting this last term. In the next step I am writing this one. I have already explained how I have got this step. So in place of this I am writing this one, which give lambda I modulus of lambda I square is norm of xi a square is equal to 0 for all high ranges from 1 to dot 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 n. Since x1 x2 x3 are the subset of orthogonal sets, these are the subset of orthogonal set of non-null vector, therefore their norms is greater than 0. Since norm of xi is greater than equal to 0, we have only one option, that is lambda I square is equal to 0 for all high ranges from 1 to n. When modulus is greater square of modulus is equal to 0, that means lambda I is equal to 0 for all high ranges from 1 to up to n. We have considered alpha 1, alpha 2, dot 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 alpha and the scalar such that linear combination of this scalar with this factor is 0. I am getting here scalar is 0. That means this x1, x2, dot 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 xn is linearly independent set. Next definition, two non-empty subset M and N of inner product space X is said to be orthogonal if X is orthogonal to Y. Okay, two sets M and N are orthogonal. That is, M is orthogonal to M, M is orthogonal to N if and only if X is orthogonal to Y for all X belongs to M and Y belongs to N. Then these two sets are said to be orthogonal. Okay, these two sets are said to be orthogonal. Next is example on orthogonality of the set. Let U equal to 1, 1, 1 and B equal to 1 minus 2 minus 3 and W equal to 1 minus 4, 3 be three vectors in R3 R. In the definition of non-linear space, in inner product space, I have taken the mapping from this to this, X cross X to C, but here I am considering the space R because R is a subset of C. Why I have not taken this space as real linear space? Because in that case the second axiom in the definition of inner product space, that is, this will be meaningless. Okay, that's why in the definition of inner product space I have considered this as C, not R. If this happen for C, then typically happen for R. Not always, but in case of inner product space, this happens. So here I am considering U, V, W, this vector in R3 R. Then you have to check whether U is orthogonal to V, or U is orthogonal to W, or V is orthogonal to W, or both 2 and 3 are correct. For that I am finding inner product of U and V. For here, if you take R, then it will be Rn. Rn is known as Euclidean space, and if the mapping is from x cross x to C, and then it will be Cn will be unitary space. Okay, so here my space is R3, so it goes to here n is my 3 Euclidean space Rn. So find out the inner product space, inner product of U and V, that is inner product of U and V, as I have defined here how to obtain inner product in my inner product space lecture. Here you have to multiply first element of U with first element of V, add up with second element of product of second element of U and V, sum with product of third element of U and V. This is this one. First element multiplied with first element, then second add with multiplication of second element of both the vector, add up with multiplication of the third vector, third element of both the vectors. On simplification you will get -4. That means inner product of UV is -4. So u is not, or u is not orthogonal to, not orthogonal. Okay, or this should be not orthogonal, not this one, not orthogonal, not orthogonal to V. Okay, correct this one. Next, inner product of U comma W. Again, multiply first element of U with first element of W, add up with multiplication of second element of U with second element of W, then add up with multiplication of third element of U with third element of W. I am getting here it is 0. Therefore, U is orthogonal to W. Likewise, you should find out inner product of V and W. This is again 0. That means V is orthogonal to W. That is U and V is orthogonal to W, but U is not orthogonal to V. Here U is orthogonal to V is not correct. U is orthogonal to W is correct, and V is orthogonal to W is correct. Here fourth answer is both 2 and 3 are correct. Here most reliable answer is 4. So my answer 4 is my correct answer. Okay, next one. The non-zero vector which is orthogonal to U1 equal to 2, 5, 4 in R3 is number 1, P equal to 3, 2, minus 1, Q equal to 3, minus 2, 1, and R equal to 1, 3, 2. Then here find out the inner product of this vector with this vector, again this vector with this vector, this vector with this vector. You will get inner product of this vector with this first one is 12. So these two vectors are not are non-orthogonal vectors. Again, inner product of this vector with Q is, this is Q not P, this is Q not P. Okay, this is Q. Okay, so it is 0. So these are orthogonal. Here inner product of this vector with her, which is 25. So it is again non-orthogonal. That means here my 2 is non-zero vector orthogonal to this Q. 2 is my answer. These are your home assignment. In case of any problem, you should inform me. I will help you in solving this home assignment. With that, I would like to conclude. Thank you. Remaining will be in the next lecture.